Hi, thanks for joining me. Today I'm going to be stating and proving a really important theorem to do with upper triangular matrices, and in fact the exact same theorem holds for lower triangular matrices as well. Anyway, what is this theorem? It is that if T is an upper triangular matrix, then the determinant of T is the product of its diagonal elements. So firstly, what is an upper triangular matrix? Well, it's simply a square matrix where any non-zero elements occur either on the main diagonal or above the main diagonal. So for example, if T was say a 3 by 3 matrix and it was an upper triangular, it could look something like this. So say 3, minus 2, 6, 4, 0, 8, something like that. And so in the upper triangle, kind of this guy here, that's only where non-zero information occurs, but anything else, so anything in this kind of bottom left part of the triangle must be 0, like so. Okay, it's fine to have a 0 in the upper triangle, that's fine, but as long as in the bottom triangle, so this small thing here, so just below the diagonal, we have all zeros, like so. So this is an example of an upper triangular matrix, and in fact, hopefully you can see the definition of a lower triangular matrix, and in fact this theorem holds for lower triangular matrices as well, but I claim that the determinant of T for an upper triangular matrix T is the product of its diagonal. So for example, in this case here, I'd claim that the determinant of this guy here is just the product of its diagonal, so the product of these guys here, so 3 times minus 2 times 6, which is what, minus 36. That's my claim. Let's get stuck into the proof. Okay, so the way we're going to prove this theorem is to suppose T is an n by n matrix and then proceed by induction on n. So let's look at the first case, sort of the base case n equals 1, but that's extremely boring as we'll see in just a second, so we'll also look at n equals 2 as well. So n equals 1, so suppose T is just a 1 by 1 matrix, then T of course just has one element in, let's call it little t, like so. Now the determinant of a 1 by 1 matrix is simply whatever the 1 by 1 element is, so depth of T just equals little t, and then if we look at the product of its diagonal elements, well there's only one diagonal element, namely little t, so the product of the diagonals is just little t, so we in fact verify our formula that I claimed. Bit boring in the case n equals 1, so let's look at something which is slightly more interesting, the case n equals 2. So if n equals 2, then T is something like A, B, C, D, but because it's upper triangular, we know that C must be 0, like so. So now if we just use our formula for computing the determinant of a 2 by 2 matrix, the determinant of T is just AD minus BC, but because C is 0, BC is 0, so it's just AD, but AD is clearly just the product of our diagonal elements here, so in fact we verify our claim for the case T being a 2 by 2 matrix as well. So that's kind of our base case. In fact, we only needed to do this for our base case, but this is slightly more interesting, so I thought I'd include it. Anyway, now let's assume it holds true for some n, and then let's suppose T is now an n plus 1 by n plus 1 matrix, and show that our claim also holds for T. Okay, so as I said, what we're going to do is assume our claim holds true for any n by n upper triangular matrix, which I'm denoting Tn, and then what we're going to do is consider an n plus 1 by n plus 1 upper triangular matrix, and we'll call that Tn plus 1. And because it's an arbitrary one, let's just write in arbitrary elements. So we'll have T11 being our sort of top left element, then T22 being our diagonal, T33, and so on all the way down to Tn plus 1, n plus 1, like so. Now because it's upper triangular, we know that every element here is going to be 0. So anything beneath this diagonal is going to be 0, so I'm just going to draw a big 0 there, like so. And also, well, we don't really know what's in the upper half of our triangle. There could be zeros, but there's allowed to be non-zero elements as well. So say T12, T13, and so on, all the way up to T1, n plus 1, and so on, like so. Now the key to this is we want to use our assumption that our claim holds for n by n matrices, and then use that to help us prove the case of n plus 1 by n plus 1 matrices. And the way we're going to do that is just look at this guy here, this kind of thing in the box here, and notice that that is an n by n upper triangular matrix because, well, it's clearly n by n because we have an n plus 1 by n plus 1 matrix, but we've gotten rid of one row and one column. And it's also clear to see that everything beneath the diagonal is also 0. So we know the determinant of this guy here, so if I call this thing in the box Tn, we know that depth Tn is just the product of the diagonals, so namely the product of its diagonals, which is T22, T33, and so on, all the way up to Tn plus 1 n plus 1, like so. So now we want to compute the determinant of Tn plus 1. And well, using that what we know about det of Tn, we can hopefully work out what det of Tn plus 1 is. But recall that sort of a formula for determinants is we do this guy here, so T11 multiplied by the determinant of this guy here. Then we look at the next guy in the column, next term in the column, so 0, and then we multiply 0 by the determinant of, let me try and draw this correctly, so this guy here with this kind of guy here. So basically you eliminate the row and column, and then you multiply that number there by this thing here, and you subtract that off. Then you do the same with this, except you add it on, and subtract 0, add 0, subtract 0, and so on. But the key to this is that you're just adding and subtracting a bunch of zeros, and that's just not going to change your sum. So in fact, the determinant of Tn plus 1 is simply this guy here multiplied by the determinant of what's in the box, because anything beneath it is just going to contribute 0 to our sum when we compute our determinant using our determinant formula. So the determinant of Tn plus 1 is simply T11 times the determinant of what's in the box, so T11 times det Tn, but we know that det Tn, by our assumption, is just this thing here. So all in all, we get that det Tn plus 1 then is just T11 times T22 times all the way up to Tn plus 1, n plus 1, or in other words, the product of our diagonal elements, like so, and that proves our claim. I hope that's all made sense. A kind of fundamental theorem to do with upper triangular matrices, and as I said, you can use the exact same proof pretty much to prove the same claim holds for lower triangular matrices. Anyway, I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.